Frankfurt, Germany, May 3rd, 1937. The world's largest aircraft, the Hindenburg, prepares to depart for New Jersey. The airship's tanks are full of hydrogen and nitrogen, fueling its 11th transatlantic flight to the United States.
For nearly 90 years, the Hindenburg disaster was shrouded in mystery, blamed on sabotage, weather, or sheer misfortune. But in 25, scientists finally cracked the code. A forgotten film, cutting-edge experiments, and chilling physics reveal the real cause. The truth isn't what you think, and it changes everything we believed. The vault opens, 25 revelations. For nearly 90 years, the skyborne inferno of the Hindenburg lingered as one of the world's most iconic disasters. And yet, for all the smoke, for all the flame, the exact spark that doomed the airship remained cloaked in uncertainty. But in 25, that began to change. At Caltech, Greek-American scientist Konstantinos Giapis, along with a team of Greek researchers, reopened the case, not out of curiosity, but out of determination to confront a question science had long set aside. What exactly ignited the Hindenburg? They weren't interested in theories, they wanted proof. Their breakthrough came not just from lab work, but from amateur footage, a rare, dusty reel rediscovered in a family archive. Shot by Harold Schenk on 8mm film, it captured something the original newsreels missed: the entire 4-minute window leading up to the disaster, from the moment the airship began its descent to the instant it erupted. For the first time, investigators had clear visual continuity, from nose to tail, of the critical period before ignition. With that footage in hand, Giapis' team could now synchronize events with electrical theory and chemical behavior. This wasn't just a rewatch, it was a reconstruction. They returned to the lab. They measured, simulated, fired artificial sparks into scaled replicas of the Hindenburg skin and frame. They tested how static charges could accumulate and discharge across separate conductive materials. The physics pointed in one direction, and suddenly, nearly a century of speculation gave way to something sharper, something terrifying in its simplicity. The true cause wasn't sabotage, it wasn't explosives, it wasn't even malice. It was science left unguarded. What Giapis and his team discovered rewrote the Hindenburg narrative, not with guesswork, but with precise alignment between data, timing, and physical evidence. They isolated the conditions, recreated the charge buildup, and even simulated the exact 4-minute delay that separated the rope drop from the first spark. For decades, every theory was missing the same thing: a full picture. Now, with real footage and real experiments, the picture was whole. The spark that ignited the Hindenburg had finally been found. And it wasn't in the fuel, the frame, or the paint. It was in the electricity dancing between skin and skeleton, hidden from sight, quietly building toward catastrophe. But what triggered that charge? The answer takes us into storm clouds and steel cables, into the invisible forces that turned a landing into an explosion. That's where the next revelation lives. The ignition spark, static secrets revealed. For years, static electricity was a suspect in the Hindenburg's destruction, dismissed, debated, never confirmed. It lacked precision, lacked proof, until now. In 25, researchers proved what many had suspected. The Hindenburg became its own capacitor. As the airship prepared to land in Lakehurst, New Jersey, on May 6, 1937, it entered humid air and a light drizzle, ideal conditions for electrical buildup. The ship's skin, coated in a metallic dope, acted as one conductor. The internal frame, electrically isolated from the skin, acted as another. As wet mooring ropes were dropped to the ground, they allowed the frame to begin equalizing its charge with the earth, grounding it. But the skin? It remained suspended, insulated by rubber pads and dry gas bags, holding its charge like a battery waiting to snap. It was a perfect storm of materials and timing. Giapis' lab tests confirmed the theory. The ship's envelope could build a high-voltage potential between its outer shell and inner frame. The act of lowering ropes to the ground partially grounded the structure, but left the outer skin highly charged. This imbalance, under the right conditions, would arc, a high-energy spark snapping through gas-rich air. But why the 4-minute delay? The answer was chilling. It wasn't an immediate discharge. Instead, the voltage climbed gradually as the ship floated and the humidity shifted. When the charge finally reached its threshold, it sparked at a weak point, a site where hydrogen had slowly been leaking. And that was the match. Observers had noted strange ripples in the fabric along the stern before the fire, as if gas was escaping. The airship had been tail-heavy, despite trimming. Small clues of a hidden hydrogen leak, invisible, odorless, undetected, until it met the static. When the spark came, it ignited the leaked gas in the stern. The fire erupted with sudden force and unimaginable speed, racing through the flammable envelope. And within 90 seconds, the Hindenburg was nothing but steel bones on scorched earth. No bums, no saboteurs, just electricity, gas, and human oversight, converging in the worst possible way. As the science clarified, the tragedy became even more human. The Hindenburg wasn't destroyed by evil, but by physics misunderstood. And now that we understand it, the story of the fire isn't just solved, it's finally complete. The invisible leak, hydrogen's lurking danger. Before there was flame, there was silence. The Hindenburg's final approach seemed routine. Passengers gathered near windows. Crew prepared for landing. The ground team waited with ropes in hand. But something unseen had already begun to unravel the world's largest airship. Hydrogen, the lifting gas that had carried the Zeppelin safely across the Atlantic, was slowly seeping out, and no one noticed. There were hints, small, unsettling clues missed in the moment. Observers on the ground noted fluttering fabric panels high near the tail. The envelope rippled unnaturally, as if air, or gas, was leaking out beneath the surface. Inside, crewmen reported that the ship was tail-heavy, requiring repeated trimming with ballast to keep it level. These were red flags, but in 1937, they were simply written off as routine. The Hindenburg wasn't new to minor hydrogen issues. Small leaks were almost expected in such a massive craft. But this one was different. It was larger, persistent, and likely began hours earlier, possibly during or just after the final turn toward New Jersey. Worse still, the ship's detection systems were primitive. There were no alarms for small hydrogen leaks, no sensors lining the 16 gas cells, no redundancy. The crew had no idea they were floating a slow-leaking bomb. And it wasn't just the gas, it was where the gas had gathered. Jaiopas's team, using detailed simulations and wind pattern analysis, showed that the leaking hydrogen likely pooled near the upper rear quadrant, where a static discharge would soon ignite it. This region of the ship was especially vulnerable. Tight spaces, thin skin, and concentrated gas. As the ship hovered, that invisible danger grew with every second. The paint on the skin, composed of flammable compounds, made the airship not just buoyant, but dangerously combustible. But even then, the flammable skin wasn't enough to start a fire. It was the hydrogen leak, and the perfect atmospheric condition that allowed the buildup of static charge, that turned the Hindenburg into a powder keg. What's tragic is how normal everything still looked. Passengers smiled, crew gave tours, children leaned out to wave. They were living inside a time bomb, and the countdown had already begun. No one could see the hydrogen escaping, no one could hear it. But somewhere above them, a storm was quietly forming, built not of weather, but of physics and human oversight. And when that spark finally came, there was no stopping what followed. Timing is everything. The 4-minute countdown. If the Hindenburg had landed 4 minutes earlier or 4 minutes later, history might have written a different ending. But instead, it landed exactly when the physics were right, and the danger was invisible. At 7:21 p.m., the Hindenburg's crew began releasing the landing ropes. This routine maneuver dropped soaked lines to the ground crew, anchoring the massive ship and beginning the descent. But this time, the weather added a twist. A light drizzle coated the ropes, creating a conductive path from the frame to the ground. This should have been harmless, but the Hindenburg's skin, still electrically isolated, remained charged. Now, one part of the airship was grounded, while another held thousands of volts of static electricity. It was a floating capacitor, and the countdown had begun. Jaiopas's lab found that the voltage needed to arc between skin and frame could build gradually in high humidity, especially as wet ropes grounded the inner frame while the skin stayed airborne. That charge didn't release instantly. It took time, roughly 4 minutes. During that time, the trapped hydrogen was swirling invisibly through the upper aft section of the ship. A passenger looked out and waved. On the ground, the crew pulled the mooring ropes taut. Then it happened. A single spark. It likely arced from the charged outer skin to a grounded strut near the stern, right where gas had leaked. It was invisible, nearly silent, but when it touched that hydrogen, the reaction was instantaneous. A thin blue flash ignited the tail section. Flames raced forward like a dragon coiled in fabric. In just seconds, the entire rear of the ship was ablaze. Witnesses described it as a lightning strike from within. Passengers screamed. Cameramen dropped their tripods. Crew ran toward exits, but many never made it. By the 90-second mark, the Hindenburg was gone. Its skeleton collapsed into the field, engulfed in fire and smoke. 36 people lost their lives, and an entire era of airship travel died with them. But it wasn't random. It was timed, predictable, mechanical, scientific. 4 minutes of slow, silent buildup, then fire, then history. The delay that once baffled engineers and survivors alike now had a name: electrostatic discharge lag. The final piece of the puzzle that linked static, hydrogen, and catastrophe. And that timing, so precise, so lethal, transforms the story from tragic accident to calculated inevitability. Dismissing sabotage, myth meets science. For decades after the Hindenburg exploded in 1937, the question on everyone's mind was simple and deeply human. Who did this? Was it a bomb? Was it sabotage? Was there someone on board who wanted the ship to fall? It wasn't just idle talk. The political climate at the time fueled the suspicion. Nazi Germany had built the Hindenburg as a floating symbol of its technological power. It carried swastikas on its tail. And it had just flown over New York, a city filled with critics of the Third Reich. To many, the fire wasn't just a tragedy, it was a statement. Investigators in 1937 interviewed passengers, crew, and ground staff. They looked for signs of explosives, chemical triggers, or incendiary devices. They questioned saboteurs. Some pointed to disgruntled workers, others to anti-Nazi operatives. A few even hinted that the Germans themselves may have destroyed the ship to avoid letting it fall into American hands. But no one was ever charged. No device was ever found. Still, the theory refused to die. Books and documentaries revisited the idea, especially in the Cold War years when sabotage made for compelling storytelling. But then came 25, and science had something to say. With the reanalysis led by Konstantinos Giapis and his international team, sabotage finally gave way to electrical and mechanical fact. Using modern simulations, they could now align the physical behavior of the fire with the materials, conditions, and most critically, the timeline. What they found was this: the fire did not begin in a way consistent with explosives. There was no shockwave, no directional blast, no pattern of shrapnel, displacement, or sudden outward force that typically accompanies bombs. Instead, what appeared in the 8mm recovered footage was a brief flash, a glow from the upper stern, and then a racing fire line, consistent with a gas ignition, not a device. The damage also didn't match a central explosion. It started high and aft, not deep inside the passenger areas or fuel lines. Science, at last, overruled suspicion. Sabotage wasn't just unlikely, it was now mathematically incompatible with what had actually occurred. The truth? There were no villains, only systems poorly understood. The hydrogen, the skin, the ropes, the weather, each a piece of a silent mechanism leading to ignition. No human actor was needed. No hand reached for a match. And perhaps that's the hardest truth to accept, because it means no one had to sabotage the Hindenburg. The ship was always doomed, by its own design. Skin deep, the paint hypothesis revisited. In the aftermath of the disaster, another theory emerged, one that stuck in the public imagination for decades. If not sabotage, perhaps the problem was on the surface, literally. The Hindenburg's skin, like most airships of the era, was coated in a dope, a mixture of iron oxide and aluminum powder that sealed the fabric and added strength. It made the silver sheen iconic, but it also made the surface flammable. In time, some began to suggest that the Hindenburg was coated in thermite, a compound that, under the right conditions, burns hot enough to melt steel. This theory gained traction in the early 2000s, when television shows like Mythbusters tested it. Their small-scale replicas showed that, while the skin could burn rapidly, It didn't explain the scale or speed of the Hindenburg's destruction, nor could it ignite without an external spark. Still, the theory hung around. But in 25, Giappis's lab finally put the paint hypothesis to rest, not with speculation, but with chemistry. Their analysis confirmed that the paint mixture, though flammable, did not have the right ratios or densities to act as thermite. It could burn, yes. And once the hydrogen exploded, the skin's coating absolutely accelerated the fire's spread. But it did not cause the fire. It wasn't the match. It was the kindling. Like dry leaves in a forest fire, the paint helped carry the flames across the hull, faster than the crew could react. But without the hydrogen leak and the static spark, it would have done nothing. This finding is crucial. It reframes the paint not as a culprit, but as a contributing factor, a design flaw in an already volatile system. The Hindenburg wasn't destroyed by a single cause. It was a compound catastrophe. One misjudged material, one overlooked gas leak, one ungrounded charge. Together they wrote the airship's obituary. It's a sobering lesson. Even the most iconic disasters rarely have one villain. More often they are a chain of ignored details, each small on its own, but deadly in sequence. And while the skin didn't ignite the disaster, it helped turn it into history's most haunting airship tragedy. Weather or foolishness, stormy skies and static risk. The skies over Lakehurst, New Jersey, were gray on May 6, 1937. As the Hindenburg approached its mooring tower, a light drizzle fell, soaking the field, the ropes, and the skin of the airship. It was the kind of weather that feels forgettable, mild, unthreatening, but in retrospect, it was charged with danger. For years, people debated whether the weather played a role in the disaster. In 25, the answer came back clear. Absolutely. Through high-resolution atmospheric modeling and historic meteorological data, Giappis's team recreated the exact conditions at Lakehurst during the Hindenburg's descent. What they found confirmed a fatal alignment: high humidity, persistent rain, and a moisture-laden atmosphere, all perfect for building and sustaining static electricity. It wasn't the storm that doomed the ship. It was the invisible forces inside the clouds, soaking into the fabric of the airship and turning every action, every droplet, every wet rope into a step toward catastrophe. The Hindenburg, like most airships of its era, was not equipped for modern static discharge protection. While it had some grounding protocols, they were crude by today's standards. There were no integrated systems to balance charge between the skin and frame, no lightning rods, no discharge wicks. Instead, it relied on routine, on trust, and on weather behaving. It didn't. As the airship floated, mooring lines were lowered. These ropes became conduits. Soaked in rain, they grounded the inner frame of the ship to the earth. But the outer skin, isolated by design, remained electrically charged. This is where the real danger hid. Giappis's team discovered that the skin acted like a floating capacitor, storing charge from its contact with humid air, rain friction, and internal movement. As the grounded frame began to balance with the earth, the skin's retained charge had nowhere to go, except through a spark. A spark that needed just one condition to ignite: leaked hydrogen. Many disasters require dramatic failure. This one came from small oversights, stacked precisely. The weather wasn't just an unlucky backdrop, it was an active participant. It primed the Hindenburg for ignition, down to the second. And so the light drizzle, often dismissed as irrelevant, became the conductor in a deadly symphony of chemistry, physics, and flawed design. Today, no aircraft would fly or land without understanding this. Aviation now builds for static grounding, atmospheric monitoring, and redundancy. But in 1937, that knowledge didn't exist. And in its absence, weather didn't just surround the Hindenburg, it set it on fire. Inside the moment, amateur footage unlocks truth. The explosion of the Hindenburg was one of the first disasters caught on film. News cameras, stationed to record its arrival, captured the now iconic footage. A sudden burst of flame, the airship falling, people fleeing across the tarmac. But all those reels had one problem. They began only after the fire started. The world saw the fall, but no one had seen the final moments before the spark. Until now. In late 24, an unexpected discovery surfaced. A family in New Jersey, sorting through an old attic box, found a reel of 8mm film. The footage was taken by Harold Schenk, a bystander with a personal camera who had filmed the Hindenburg's entire final descent, from the moment it appeared over the trees to the second it exploded. The footage, long forgotten, had sat undeveloped in a steel canister for over 80 years. Once digitized and analyzed, it became the missing puzzle piece. The film showed continuous motion from nose to tail during the critical 4-minute window before ignition. Jayapas's team could now align visual behavior with scientific modeling with unprecedented precision. They spotted the fluttering fabric, the subtle tail wobble, the moments when the mooring ropes hit the ground. They measured the timeline, matched it to frame-by-frame simulations, and pinpointed the exact second the electrostatic conditions peaked. The spark didn't come randomly. It came exactly when the physics predicted it should. Even more startling, the footage visually confirmed the fire's origin point, near the upper rear fin, just where the hydrogen leak was believed to have concentrated. It ignited outward, not inward. It expanded along the hull, not through the passenger compartment, and it moved like a gas-fed fire, not a detonation. All these patterns, once inferred, were now visible. For historians and scientists alike, it was a revelation. For the first time, technology and eyewitness evidence didn't compete. They aligned. More than that, it reframed the entire narrative. The tragedy was no longer a shadowy question mark wrapped in rumor and theory. It became a scientific event with a name, a cause, and a timeline. It moved from myth to mechanics, and it proved something remarkable. Sometimes, the key to solving history's greatest mysteries isn't in the lab or the archive. Sometimes it's in a forgotten reel of film, sitting in an attic, waiting for someone to look. And with that footage, the final moments of the Hindenburg finally came into focus, not just as spectacle, but as understood reality. Aftermath's echo, airships end, and air travel's wake. In just 90 seconds, the Hindenburg was reduced from a shining symbol of airborne luxury to a skeletal wreck smoldering in a New Jersey field. The flames didn't just consume an airship, they consumed an entire era of aviation. The numbers were sobering. 36 people lost their lives. Many burned or crushed beneath twisted aluminum girders. Survivors carried injuries that never healed. And the world watched in horror as the disaster looped on theater screens, in newspapers, and on radio, the first disaster broadcast live as it unfolded. Public trust in airships didn't just crack, it collapsed overnight. The Hindenburg had been the pride of German engineering, a floating hotel that glided across the Atlantic in comfort and silence. But in the fire's aftermath, even the name Zeppelin became a symbol of disaster. Orders for future airships were canceled, designs were scrapped, hangars were shut down. In their place rose something heavier, louder, but ultimately safer: the airplane. Until 1937, fixed-wing aircraft were still struggling to match the reliability and comfort of airships. But the Hindenburg's fall changed the landscape instantly. It handed the future to planes, not because they were better, but because they no longer had to compete against a system people could no longer trust. The world moved on, but the Hindenburg never faded from memory. It lingered as a cultural icon, a cautionary tale. Its fall was replayed in history documentaries, classroom lectures, and endless speculation. People debated sabotage, blamed the Germans, questioned the materials, and through it all, one truth remained frustratingly out of reach. What exactly caused the fire? Now, in 25, we know. It was not political, not criminal, not cinematic. It was scientific, predictable, a chain of overlooked risks that aligned perfectly: skin, gas, weather, and time. That makes the tragedy feel even heavier, because it wasn't inevitable, it was preventable. And in understanding that, we begin to see the true legacy of the Hindenburg, not just as a disaster, but as a turning point, a moment that killed one technology and gave birth to another. It didn't just end an airship, it rewrote the rules of flight. The hard lesson: safety, oversight, and vigilance. The Hindenburg disaster has always lived in the shadow of myth. For nearly a century, its flames were seen through lenses of drama, scandal, or conspiracy. But in 25, that shadow finally lifted. We now know the true cause: a hydrogen leak, static buildup, a delayed electrical discharge, and flammable materials. No villain, no bomb, just conditions, physics, and human misjudgment. It's tempting to view this new clarity as closure, but in truth it's something more important, a lesson. The Hindenburg taught us, painfully, that aviation safety cannot tolerate ambiguity, that a small oversight in weather, or materials, or discharge protocols can cascade into catastrophe. The disaster wasn't just about a failed landing, it was about systems failing to talk to each other. The hydrogen system didn't talk to the electrical behavior of the skin. The landing procedures didn't consider weather-induced conductivity. There were no alarms for leaks, no static discharge pathways between skin and frame. The result wasn't one big failure, it was a dozen small ones, perfectly aligned. And that's where modern aviation took its cue. In the wake of the disaster, engineers began rethinking design from the ground up. Today's aircraft are built with redundant grounding systems, static wicks, real-time leak detectors, non-flammable materials, and computerized monitoring that tracks atmospheric conditions every second of flight. Those safeguards trace their DNA back to Lakehurst, 1937. The Hindenburg became a case study in what not to do, and because of that, millions of lives have been protected, not from sabotage or bombs, but from the quieter, slower dangers that hide in plain sight. But the lesson goes deeper than engineering. The Hindenburg reminds us that tragedy often arises not from malice, but from neglect. That science must always chase the answers, even decades later. That truth, once buried in ash and misdirection, can still rise when we apply the right tools. In 25, truth finally caught up with myth. And while that doesn't bring back the lives lost, it honors them by ensuring we never make the same mistakes again. Because in aviation, as in life, vigilance wins where hubris fails. And the Hindenburg's final gift isn't fire or fame. It's the quiet warning that echoes into every cockpit, every design table, and every flight. Always ask, always test, never assume. No bombs, no villains, just hydrogen, static electricity, and fatal oversights. In 25, science solved the Hindenburg mystery with precision and finality. It wasn't conspiracy, it was preventable tragedy. And its lesson echoes through modern aviation. Safety is never an accident. The skies are safer today because we finally listened.